Good morning, everyone. 4.1 Angles and Angle Measure Part 2. Let's do a little startup review from last lesson. Okay. Explain how you convert from degrees to radian measure and vice versa. So we use conversion factors. Remember, from radians to degrees, we multiply by 180 degrees divided by pi. Okay? From degrees to radians, we multiply by pi over 180 degrees. Here's a tip. Also, you can use our basic angles. Pi over 6, these you should commit to memory. Pi over 6 is 30 degrees. Pi over 4 is 45 degrees. Pi over 3 is 60 degrees. Okay, pi over 2 is 90 degrees. Pi is 180 degrees. 2 pi is 360 degrees. Okay, so these are the main ones that you should have committed to memory. Let's convert negative 750 degrees to radian, measure as an exact value, sketch a graph in standard position. So negative 750, remember, big deal, matters that you have that degree sign. Use our radians to degrees conversion factor. Okay, reduce that, I get negative 25 pi over 6. Okay, how do I think about this? Well, you can think about pi over 6 as 30 degrees, and you go around in the, what's negative, so you go around clockwise direction, and you do pi over 6 25 times. That's a lot to think about. Let's think about it this way. So I'll put this in blue here. Think, I'm going to pick the closest major angle. I usually pick in terms of units of pi, radians. So in this case, I think of negative 24 pi over 6. That's really close to negative 25 pi over 6. Negative 24 pi over 6 is the same as negative 4 pi. That's 2 full rotations clockwise. But then I need pi over 6 more because I'm going to negative 25 pi over 6. Okay, I want you to think this way when you're sketching things in standard position, so it makes it a lot easier to think about. So let's do it. I'm going to go 2 full rotations, then pi over 6 more. Pi over 6 more is 30 degrees more. Okay, so let's start here. We're going clockwise because this is a negative angle. So 2 full rotations, negative 4 pi, and then pi over 6 more. So 1 rotation, 2 rotations, and then pi over 6 more, which is 30 degrees, right about there. Okay, draw your terminal arm right there. Sorry, initial arm, terminal arm. Okay, that is theta equals negative 25 pi over 6. More startup. Convert each angle to degree measure, then round to the nearest tenth if necessary. Sketch a graph. 2 pi over 3. You can multiply this by pi over 180, Or I know right away I can convert this in my head. Mental math is that pi over 3 radians, pi over 3 is 60 degrees, so 2 pi over 3, that's 120 degrees. So this one you should be able to do by mental math. Okay, so I think of it this way. Pi over 6 is 30 degrees. Oops. Sorry, folks. Pi over 3 is 60 degrees. So 2 pi over 3 is 120 degrees. That's what I'm thinking in my head. Okay? Let's sketch the angle in standard position. Okay, I have my initial arm. This is a positive angle. I'm going in the counterclockwise direction. Okay, 120 degrees. So that's past the 90 mark and then 30 more right there. Okay, there's my terminal arm. Theta equals 2 pi over 3. Negative 12.1 radians. This one I need to convert by multiplying by 180 degrees divided by pi. I get negative 693.3 degrees. Okay, how do I think about this one? Well, I know one full rotation is negative 360. And then I have negative 333.3 degrees more to go to get to negative 693.3 degrees. It's a negative angle, so I'm going in the clockwise direction, folks. Okay, so I start here, initial arm, one full rotation in the, clockwise direction. Okay, clockwise direction, one full rotation, then 333.3 degrees more. Okay, so that's going to take me, here's 90, 180, 270. Okay, and then I need about 63.3 degrees more, so that's going to take me right about there. Okay, and that is theta equals negative 693.3 degrees. Next one, determine how many radians as an exact value there are in each of the following quantities. The second hand of a clock moves 20 seconds. We know that's out of 60 seconds on a clock, right? So we can figure out how many radians. So if it's 20 over 60, right, and we know that 2 pi radians is a full rotation of the clock, that's 40 pi over 60, and that's 2 pi over 3. Okay, oh, it just says radians, but if I ask you what is this in degrees, 120 degrees, right? The Earth's rotation in 16 hours, so this is out of 24 hours, right? 16 out of 24. What fraction of that, of the full rotation, 2 pi is it? Well, that's 32 pi over 24, and that's 4 pi over 3. A runner completing 15 laps of a circular track. One lap is 2 pi radians, so 15 laps is 30 pi radians. Okay, explain what a coterminal angle is and what a principal angle is. Okay, a coterminal angle is an angle in standard position with the same terminal arm. So example, pi over 2 and 5 pi over 2. Let me give you an example in degrees. Or 150 degrees and 510 degrees. Okay. A principal angle is the smallest positive rotation angle of all possible coterminal angles. Okay, there we go. State one positive and one negative coterminal angle for 495 degrees. Identify the principal angle. So remember we do this. Remember our general form in degrees, theta plus 360 degrees times n. I like to use this integer method. So n is an element of all integers where n does not equal 0. So 495 degrees. Let's plug 495 right here. This is where 495 goes. And pick values for n. 495 plus 360. Let's do n equals negative 1. That equals 135 degrees. Let's do one more. One positive, one negative. That's my positive one. If I go to negative 2, this is n equals negative 2. I get negative 225 degrees. The principal angle is the smallest positive rotation angle of all possible coterminal angle. The smallest possible rotation angle, this is my principal angle. This meets the definition, principal angle. How could you write an expression to write all possible coterminal angles of 495 degrees? Well, we could just leave it in terms of like this. So if I have my general form here, theta plus 360n, where n is an element of all integers, n does not equal 0. That's my 495 degrees plus, leave it in general terms, the n value, and stipulate that n must be an element of all integers and n cannot equal 0. So this is my expression, right? Expression for all possible coterminal angles. Next page. Let's do a bit more on coterminal angles, okay? This will come in handy when we are solving trigonometric equations and we need to state a general solution. So we'll practice this a little bit, practice this on your own, and then when we come back to it in trig equations, you'll see how useful this is. Example, state an expression for all possible angles coterminal with each given angle. This is called general form. So identify all angles that are coterminal and are within the given domain. So let's do this. Here's the angle that I start with, negative 500, and then state all possible coterminal angles within each given angle. Identify all angles that are coterminal within the given domain. Okay, so again, for this page, there's two formats, right? Theta plus 360n, where n is an element of integers, n does not equal 0, or the radian version is 2 pi n, where n is an element of integers, n does not equal 0. Okay. So for negative 500, I do negative 500 plus 360 degrees n. N is an element of integers. N does not equal 0. Okay, let's take a look here. So negative 500 for n equals 1. Hang on, folks, sorry. For n equals 1, so that's negative 500 degrees plus 360 degrees times 1. That equals negative 140 degrees. That's still within my domain here. Okay. N equals 2. Negative 500 degrees plus 360 degrees times 2. That is 220 degrees. If I go n equals negative 1, it'll take me outside of this domain on the negative side. If I go n equals 3, it'll take me outside of the domain, which is 360 degrees. So these two angles are all the angles within my domain here. Okay, so be able to do that. Identify a restricted domain. So there's a restricted domain, and then identify the coterminal angles within that restricted domain. Next one, 650 degrees. 650 degrees plus 360 degrees times n. N is an element of integers. N does not equal 0. Okay, for n equals, this one has a bunch of them. N equals negative 1. That's 650 degrees plus 360 times negative 1 equals 290 degrees. N equals negative 2. Okay, so we got to keep one more negative with the n values to get to our negative value. So okay, so n equals negative 2. That's 650 degrees plus 360 degrees times negative 2 equals negative 70 degrees. N equals negative 3 plus, that's 650 degrees plus 360 degrees times negative 3, and that equals negative 430 degrees. If I go n equals negative 4, that's outside of my domain. So I'll stop here. Also, the original angle, 650 degrees, that's within my domain, right? 650 degrees. Okay, so all the angles that are coterminal within the given domain, 650, 290, negative 70, and negative 430. Okay, 9 pi over 4. Okay, I have 9 pi over 4 plus 2 pi n. So I'm going to use the radian version of this. N does not equal, or n is an element of integers. N does not equal 0. Okay. Let's do this, folks. This one, let's change this to a fraction with a denominator of 4. That's like saying 8 pi, negative 8 pi over 4. 12 pi over 4. Okay. Okay, so I can rewrite this like this: 9 pi over 4 plus 8 pi over 4 times n, where n is an element of integers, n does not equal 0. Okay, n equals -1. What do I got? 9 pi over 4 plus 8 pi over 4 times -1 equals, well, that's pi over 4. So that's one coterminal angle. If I go to n equals -2, that's 9 pi over 4 plus 8 pi over 4 times -2. That's -16 pi over 4 plus 9 pi over 4. That's -7 pi over 4. If I go to n equals -3, that's outside of my domain. If I go the other way, this way, if I go n, remember n can't equal 0, you're just going to get the same angle you started with, 9 pi over 4, right? If I go to n equals +1, then I'm going to be outside. If I have n equals +1, that's 17 pi over 4. That's outside of my domain on the positive side. Okay, so we start with 9 pi over 4. Okay, it says identify all angles that are coterminal and are within the given domain. So coterminal with itself, another one, pi over 4, -7 pi over 4, so 3 angles total. Okay, next page, folks. Let's think about this concept, arc length. A common application of radian measure is arc length. Recall, radian measure equals arc length forming the angle divided by the length of the radius equals arc length divided by the radius. So if I have my circle like this, okay, so I form an angle with 2 rays, and then in red, this is the arc length of arc forming the angle. So this is my angle theta. That's my angle theta. This is my arc length. This is my radius r. Okay, and this is my angle measure in radians. Okay, here's the formula. Therefore, theta equals a divided by r, where theta is the measure of a rotation angle in radians, a is the arc length, and r is the radius, just like I showed you in the diagram. Remember, theta must always be in radian measure and represents the central angle. So when you are doing arc length, folks, problems involving arc length must be in radians. How could you find the arc length if you know the central angle in radians and the radius? So we're just rearranging a formula, folks. Theta equals arc length divided by radius. Therefore, arc length equals theta times the length of the radius. Or, stated another way, radius equals the arc length divided by theta. Remember, theta must be in radians. Example 1, an arc length of 21.2 centimeters has a central angle of pi over 3 radians. Determine the radius of the circle to the nearest tenth of a centimeter. Let's list all the things that we're doing. What do we have? What do we need? Arc length 21.2 centimeters. Good. Our central angle theta is pi over 3 radians. Okay, pause here and think about it. Be able to be fluent on going back and forth between radians and degrees. How many degrees is pi over 3 radians without looking? Think. Okay, 60 degrees. Okay, anyway, let's keep going. Theta equals a over r. We need the radius of the circle, so that's radius equals a over central angle, 21.2 over arc length of 21.2 over radian measure of pi over 3, and it says to the nearest tenth of a centimeter, that is 20.2 centimeters. Okay, so that's my radius. Example 2, the ring road around the eastern part of the city of Regina is almost a semicircle. Determine the approximate length of the ring road from A to B to one decimal place if the radius of the circle is 4.9 kilometers. Okay, radius is 4.9 kilometers. Let's state our equation there. Central angle, approximate length of the ring road. Okay, that is arc length. Okay, on the eastern part. So this is the ring road. Ring roads are awesome, aren't they? Okay, the eastern part of the ring road. So I'm talking this part right here, roughly. Okay, it's roughly a semicircle. What is that length of the road? So we're looking for arc length. So arc length equals theta times r. Okay, what's the central angle for a semicircle or half circle? That's 180 degrees or pi radians. Okay, so arc length equals my central angle pi times the radius is 4.9 kilometers, and my arc length is 15.4 kilometers. So this ring road is approximately 15.4 kilometers long. Right, example 3. To prevent car thefts in a parking lot, security cameras are installed on the outer walls of a building as shown in the diagram below. Camera A has a recognition range of 400 meters and is programmed to travel through a detection angle theta. This angle corresponds to an arc length of 780 meters. So here's my arc length A. Theta is right here, the angle that it's swept out. And then the radius is 400 meters. For camera A, the measure of the detection angle to the nearest degree is, so I'm going to go theta equals A divided by R. Okay, and then let's plug in our values. A value is 780 over R, which is 400. And that's going to give me radians value, 780 divided by 400. That's 1.95 radians, and we need to convert that to nearest degree. So I'm going to go 180 degrees is pi radians, and that's 1.95 times 180 divided by pi, and that is rounded to nearest degree, that's 112 degrees.